So this lecture was from Thursday afternoon, and the idea was we were going to introduce a few ideas around random numbers, and I suppose the kind of things I'm hoping you take away is some idea of what a random variable is, some idea of what a probability mass function and a cumulative distribution function is, an idea of expectation as defined around random variables, and the idea of expectation of a function of a random variable. So basically, a random variable is a function that takes a set of outcomes from a statistical experiment and maps this to a set of numbers. So, whoa, what's all that about? Well, the idea is if we have a set of outcomes from tossing two coins, ranging from getting two heads to two tails and either a head and a tail or a tail and a head, we can map that onto a number. And if we use the rule number of heads, we can map these onto the numbers 2, 1, 1 and 0. And if we're being very naive about the way probability works, there are 4 outcomes. The first outcome is one of 4 of them, so the probability that we get a 2 is 1 over 4. So here we have both a random number, a mapping from a sample space to a number, and associated with it is some kind of attempt to quantify probability. So that's our idea of what a random variable is. Another way of thinking about it is it's a variable that can take on any of a number of values, and we don't know which value we're going to get. There are different ways of thinking about probability. For our purposes, it's just a number that runs from 0 to 1. And that number comes from a system of maths that obeys some axioms. It is worth pointing out, though, as you use probability, you might use it in different ways. We just used the naive definition, which is all about symmetry. If I have a dice and there are 6 possibilities, I associate a probability of 1 in 6 with each. We can think about probability as a long-run frequency thing. I toss a coin 10,000 times, I expect heads to come up close to 5,000. But it is also possible to think about subjective probability. And this is important. How do you determine the probability of a nuclear plant failing or an air traffic control system computer crashing? We've already used a couple of phrases that describe probability models in the tutorials: normal, exponential, uniform, discrete. The reason is that the naive definition of probability, this symmetry thing, if I roll a die, I get a number 1 with probability 1 over 6, it rapidly becomes useless in the real world. And what has found to be very useful, there are a whole set of families of mathematical functions that in practice seem to do a reasonable job marrying up to the way things vary in the real world. And the simplest one we can talk about is something called the Bernoulli distribution. The idea of the Bernoulli distribution, there are 2 possible outcomes. So this is a little bit like tossing a coin, but we don't necessarily want the 2 outcomes to be equally likely. So we could be thinking about the possibility that you get a virus at the weekend. So we don't want that to work like a coin where the probability is 50-50 that you do or you don't. How do we denote this? We use an uppercase Roman character to denote a random variable which can take on any of a number of values. And we denote the 2 numbers as 0 or 1. And the convention is we use the 1 if something good happens and 0 if it doesn't happen. So Z can be 1 if I get my head coming up on my coin toss. Z can be 1 if I end up at the weekend flu free. However, here's the important notational point. Once I've conducted my experiment, I use a lowercase variable to denote the actual realization of the random variable. So I can say something like the probability a random variable of unknown value takes on a particular value z, and that makes sense if you follow the notation. So I just want to unpick this carefully. The P is telling us we're trying to evaluate the probability that a random variable which can take on a number of values takes on a particular value z. It's important, it will save a lot of work later if we understand that notation. We then have something called a probability mass function, and this is just a mathematical function which I've abbreviated here using the lowercase f because it's a function that tells us what is the probability that a random variable takes on a particular value. The Bernoulli happens to be kind of ugly, but essentially it's a stepwise function. The probability that a random variable uppercase z equals lowercase z equals 1 is p, and the probability equals 0 is conventionally 1 minus p, and sometimes it's just easier to write q for 1 minus p. But essentially we're talking about z being distributed as a Bernoulli random variable with a parameter p, and if I know p I can work out q. So we need to do a couple of checks. So probability cannot be negative, so p we said had to be between 0 and 1. 1 minus p therefore is also between 0 and 1, so that's okay. The total probability that I get a head or a tail is going to be p plus 1 minus p. Well, that adds up to 1. Want to do a little illustration, you can plug in the numbers for coin tossing, 0.5, and just check that makes sense. So, to summarise this little bit of theory, a random variable denotes our sense of uncertainty about something we decide to call the outcome of a statistical experiment, and it maps some kind of sample space to a set of numbers. So for discrete random variables, what we call the probability mass function gives us a model for the probability of different outcomes. And probability can be anything that obeys some axioms. These include rules that probability must be non-negative and must sum to 1 over the entire sample space. Now, I'm introducing the idea with the Bernoulli because we're working here. It's quite a difficult thing to work with at the moment, but it's the idea of a cumulative distribution function. And we might be interested to know what is the probability that a random variable x takes on a value that is equal to or lower than a particular value of x. And this is all rather obvious for the Bernoulli, but we'll just look at the definition. So here I've said what is the probability that the random variable z is less than or equal to minus 0.001. Well, that has to be 0 because we said z can only take on values 0 and 1, so the probability it takes on a value less than 0 is going to be 0. The probability z is less than or equal to 0 has to be the probability z equals 0. Out of all those possible values we're suggesting, it's only one we care about. It's the probability z equals 0. We said that probability is 1 minus p. If I take the example, what's the probability z is less than or equal to 0.72? Again, there's only one way that can happen, and that's if z equals 0, and we said the probability that happens is 1 minus p. And finally, just to make the point, what's the probability z is less than or equal to 243? Well, we're asking what's the probability it's either 0 or 1, both of which are less than 243. Well, that has to be 1. As it says, I'm not saying this is a particularly useful thing for the Bernoulli, but we're just introducing the definition which we'll use. We can sketch this function as follows. So we looked at possibilities. What's the probability it's less than minus 0.01? What's the possibility it's less than or equal to this? And we carried that on a long way and said what's the possibility it's less than or equal to this? And the function's just mapping this. Any of these numbers here probability that z is less than or equal to those is 0. Any of these numbers here, probability we have a random variable less than or equal to that is given by 1 minus p, and likewise the probability is anything above, it's less than, any number we pick above 1, well, that has to happen because it can only be 0 or 1. In the lecture we just ran through a little preamble thinking about how we have lazy ways of calculating the mean of some numbers, and we could just use the definition directly, 1 over the number of numbers multiplied by the sum of all the numbers. But there's a shorthand way of doing this. We can take 2 over 9 and multiply it by the 1. We can take 5 multiplied by 1 over 9 multiplied by the 2, and 2 over 9 multiplied by the 3, and it's a different way of working out that weighted average. And as we said in the lecture, if that's something you've done before, that's very handy. It'll explain what's coming next. If you've never done before, don't worry about it. Because the idea we want to look at is the idea of an expected value. I'm going to illustrate this for a dice throw, and we're going to ask what's the expected value of a dice throw. So the scenario is the random variable x can take on any of 6 values. The probability it takes on any one of those values is 1 over 6 by the naive definition. And here's our definition of expectation. It is the sum over all possible values of x multiplied by the probability that the random variable took on that particular value. Let's unpack that. Put the definition again at the top. What we're saying is here is x takes on any of these values. The probability it takes on that value is 1 over 6. And here we multiply x by f of x. Multiply x by f of x to get x multiplied by f of x. The last thing we do is sum over all 6 possibilities. So we add this to this to this to this to this to this and get 21 over 6 or 3.5. So this in a way is an average value for that random variable. How many moves do we expect to make on average if we roll a die that's a fair die with conventional numbering? And we can extend this a little bit to expected values of a function of a random variable, and the conventional notation for this is the expected value of g of x. G of x can be any function we like. It can be a mathematical function such as take the square of x. We'll use some slightly woollier functions, but the definition is very simply it is the sum over all values that x can take of g, the function applied to the realization, and the probability x took on that particular value. And again, we'll illustrate an example. We're going to play a die game, and the function is, if it's odds, I pay you that many pounds. If it's even, you pay me that many pounds. And we want to work out the value of that game. So, here again we have x taking on any of 6 values. And here we have g of x. So the rule was, if it's odds, I pay you £1. If it's evens, you pay me that many pounds. So odds, you gain 3, evens, you lose 4. So this is g of x. F of x, exactly the same as before, is 1 over 6. So we multiply g of x by f of x to give us gx f of x. And you find we have 1 over 6 minus 2 over 6 from multiplying these two numbers together. And again, as before, the summation operator tells us to sum all of these. So the expected value of that game to you is minus £0.5. So if you play that game, you expect to lose 50 pence. And without stating the obvious, if it involves gambling, that's the basic rule. You lose, they win. So here's a slightly more worked example that's going to use a Bernoulli random variable. And the idea is I am selling tickets for £1. The prize fund is £1. I sell 1,200 tickets. And you're asked to calculate the expected value of a ticket draw. So we're going to use the Bernoulli random variable. Z is 1 if we win, Z is 2 if we lose. By the naive definition, there's 1,200 tickets sold, one's going to win. So this is 1 over 1,200, and the function of Z is going to be minus 1 if we lose, we've just spent £1, plus 499 if we win, spend £1 but we win 500. So we can fit in the calculations. If I draw a 0, g of z is minus 1. The probability of getting a 0 in this draw is 1 minus 1 over 1,200. So multiply this number by this number and I get minus 1199 over 1,200. On the other hand, I might win. Z equals 1. If I win, g of z is 499. Probability I might win is 1 over 1,200. Multiply those two together, I get 499 over 1,200. To calculate the expectation, I sum these values. If I sum and simplify, I'm looking at an expected value of minus 0.58. So yet again, gambling scenario, what's the expected value of playing the game? It's negative. I think this is all a little bit trivial and light-hearted. The prize structure for the lottery is a little bit more complicated. There's more than one ways of winning different amounts. There's also uncertain allocations of the prize pool, but although it's a more complicated calculation, you could do it, and as you know, you're going to find out the expected value of a lottery ticket is negative. Another example that a lot of people have dealt with is an insurance policy. You buy an insurance policy, you expect on average to lose. The expected value has to be negative, otherwise the insurance company would go out of business, but you're prepared to pay that money because the consequences of loss are too severe, or it's the law if you're driving a car. And the point is, these are just extensions of the basic concept of the expected value of g of x. Just to point out, you can get incredibly complicated questions to be asked calculating the expected value of g of x, and the kind of places they crop up are things like health technology assessments. We want to work out the expected value of a particular therapy and work out whether it's good value for money. This is subject to uncertainty and it involves some really rather complex Monte Carlo methods. Just wanted to introduce the coursework. We will start looking at that in the tutorial on Monday, but the scenario is given to you in Supercrunchers on page 58. Kelly Cook ran an experiment for Continental Airlines to do with apologising to frequent flyers who'd had delayed flights. You're asked to do three things. The first is to summarise data on the results of an experiment. The second is to construct a randomisation test to answer the question, was the intervention effective? And we will look at a dummy scenario for this in the tutorial on Monday. Finally, you're asked to consider, to design, but not implement, a Monte Carlo study that explains what the expected value of the intervention could be to the organisation if applied generally. The whole idea is you will be given plenty of support with this. You can have as much help as you want setting up the dummy scenario. Once you've set up the dummy scenario, it should be very straightforward to apply this to the data that's come from the Kelly Cook experiment.